Okay, welcome back, everyone. Thanks for showing up today. We have a couple of minutes before the start of class. If anybody has any questions for me. Okay, so today and for the next few classes, we actually have some nice treats where we will see some really nice, clever data structures that do things, support operations in certain times that are surprisingly fast. So our warm-up today is data structures for integers. And in particular, I want to support a data structure that stores integer keys, let's say, and it supports the sorted set interface, or at least the simplified version of it that the book calls S-set, which is you want to be able to add things, you want to be able to remove things, and you want to be able to find things. And find here has a specific meaning. If X is in the set, then I actually want to find it and return it and say that it's in the set. And if X is not in the set, then I want to find, let's say, the smallest thing in the set that is greater than X. So that would be called the successor of X if X is not in the set. Okay. And we want to do this. We'll assume that the data we want to store is W-bit integers, and common values of W nowadays are 32 and 64. So that might be things that you find just the standard words in modern computers. And 128, those could be IPv6 internet addresses. Those are 128 bits. So, they're integers, a fixed length, W, but W can be, quite big. So this doesn't mean that they're small integers. All right. So what are we competing with? Well, integers, of course, are comparable. You can give me two integers, X and Y, and I'll tell you whether or not X is bigger than Y. So any of the sorted set interfaces that we have seen, you can use them, and you get all of these operations in O of log n time where n is the number of values that you're storing. Okay? So what we want to do is beat O of log n time. So let's start with the most basic thing and work our way up to faster and faster things. All right, so the most basic structure you could think of is what's called the binary I will pronounce it binary trie, but actually this word you're supposed to pronounce tree. It's part of the word retrieval. But because we also talk about things like binary search trees in this course, and in fact, sometimes when we're talking about tries, there will also be another tree. I'll mispronounce this deliberately and call it a trie, just so so you don't get confused when you're listening to me. All right. So, and here's an example where, of course, I can't do draw examples where W is 32 or 64. So here's an example where W equals 4. I know this is a little bit trivial, 4-bit integers. There's only 16 of them, so you can imagine it's not difficult to store them. But everything that I'm going to say and the examples that I do will generalize to arbitrary values of W. And let's say we want to store 3 values, 3, 9, and 12. So 3 in binary is 0, 0, 1, 1. 9 in binary is 1, 0, 0, 1. And 12 in binary is 1, 1, 0, 0. Right? That's 2 plus 1 is 3. That's 8 plus 1 is 9. And that's 8 plus 4 is 12. All right? So a binary trie is a really simple thing, not particularly fast, but it's the underlying thing that we will use for everything that we're going to do. And you think of it as, well, the elements that you want to store will be stored in leaves of this binary trie. And the binary trie is a binary tree. All the leaves are at the same depth. The depth is W. And the way you imagine reading, looking for something in this trie is you look at the first bit. If the first bit is 0, so you start at the root, you look at the first bit. If the first bit is 0, you go to the left child. And if the first bit is 1, you go to the right child. And then you look at the next bit and go to the left child or the right child, depending on whether the next bit is 0 or 1. So for instance, for this thing, we see a 0 first, so we go left. We see a 0 again, so we go left. Then we see a 1, so we go right. And then we see another 1, so we go right. And that takes us to the node that stores this value, the leaf that stores this value. And similarly, for 9, we see a 1, so we go right. Next is a 0, so we go left. Another 0, so we go left. And then a 1, so we go right. Very simple thing. Unfortunately, it doesn't do much for us. So you could imagine that it's kind of easy to add things to a binary trie. For instance, if I wanted to add, let's say, let's say I wanted to add 1. So 1 is 0, 0, 0, 1. That's the 4-bit representation of 1. Then I would start at the root and say, okay, well, I need to go left because the first thing is a 0. I need to go left because the next thing is a 0. I need to go left again because this is a 0, but there's no node there yet. And that's just because currently there's nothing in my set that starts with 0, 0, 0. And if I want to insert this, that means I have to make that node. So from this point onwards, we have to start making every node on the path. So we get a 0, 0, 0 star, and then finally 1. So that says from this we should go right. And that's where we store this thing. So adding is easy in a binary trie. Removing is also easy, right? If I wanted to remove 1 or 3, it doesn't matter, let's say 3, well, I would walk down until I find 3. If I don't find it, I can stop. There's nothing to do. And now I just want to walk back up this tree and basically get rid of a node. So first take away this node with 3 in it. And then at the parent of 3, I look to see, now that this node with 3 is gone, does this node have any children? In this case it doesn't, which means this node can go away. So I would remove this node as well. And then I come here and I say, does this node have any children now? In this case it still does have a child, this one, so I stop. So after removing 3, these 2 nodes are gone, and we get that. So that's just one pass down the tree to find the thing to remove, and then one pass part way back up until you get to the first place. In fact, it'll actually be where this process stops is just at the first time you reach a node that used to have 2 children, because you're deleting one of them, and then the other one still lives. So that's easy. Add and remove are easy. We'll worry about the running time in a second. What about find? Well, okay. Find is good. If I want to find 9, I just follow the path for 9 and I find it. And if I want to find 3, I follow the path for 3 and I find it. But that's not all find is supposed to do. Find is also supposed to work when you search for something that's not there. It's supposed to give you some answer, the smallest thing that's bigger than what you're looking for, if the thing you're looking for is not there. And so, for example, here, if I search for 4, 4 is a 0, 1, 0, 0. So the answer should be 9. But if I follow the search path for 4, so I have to follow, the first thing is a 0, and then a 1. So the search path for 4 goes down to here, but then it's stuck. There's no nodes there. There's nothing, we can't continue the search in this case. So the plain old binary trie doesn't solve the problem, because it doesn't help us when we're searching for things that are not there. It doesn't give us any sort of useful result. So let's rethink that. Let's do binary trie plus what are called jump pointers. And a linked list. So at the bottom level here in this trie, we have a bunch of values, the values that are being stored in our sorted set. let's put them into a doubly linked list. I won't explicitly draw all of the fields for pointers, but we understand doubly linked lists well enough now that we can imagine that, yes, each node down here has a couple of extra fields. Maybe they're circularly linked. But don't worry about the details. The important thing is from one node we can get to the one before it and the one after it. So that kind of helps. I mean, it means that if we've managed to get to 3, we know that the next biggest thing is 9 and the next smallest thing is 1. But it still wouldn't help us, for instance, if we go searching for 4, because the search for 4 falls out of the tree here. And here's where the clever idea comes from. So if we look at the nodes in this tree, there's 2 kinds of nodes. There's the ones that have 2 children, like this one and this one. And then there's the nodes that have only 1 child, like this one and this one. This is one with 2 children, it's okay. So the things that have only 1 child, these are nodes, so they have room for 2 pointers, right? They have room for a left child and a right child, and sometimes one of those pointers is not used. So what we'll do is use it for something useful. So in a node like this, if you do not have let's say this node doesn't have a right child, well, it has some child, otherwise it wouldn't exist at all. We would have taken it away. So if it doesn't have a right child, that means it has a left child. If it has a left child, that means there's something in the left subtree here. And in particular, there's a largest thing in the left subtree. So in this case, the largest thing in the left subtree is 3. So that right child pointer, instead of pointing to some node here, it will just point directly to 3. This one here, same thing. It has no right child, so it points to the largest thing in the left subtree. In this case, there's only one thing, so it points directly to 9. This one has no right child, so it points to the largest thing in the left subtree. In this case, it's 12. And these nodes here, same thing. This one has no left child, so it'll point to the smallest thing in the right subtree. There's only one, so that's kind of easy. Same thing with this one. This has no left child, so it'll point to there. This one has no left child, so it points to there. This has no right child, so it points to there. All right, so that's a binary tree plus the jump pointers. These are pointers where there's a child missing that they point directly to the bottom list. And then there's a linked list. So in the bottom, the elements are stored in a linked list in sorted order. All right, does that allow us to do find now? Well, let's see. Let's say I go searching for 4. Well, I search for 4, so that should go here. And next thing is a 1, so I should go to the right child. But there's no right child, there's just a jump pointer to the right. But if I follow that jump pointer, what I find is the largest thing in the left subtree. Okay, so that largest thing in the left subtree is actually the largest thing in my set, which is smaller than what I'm looking for. Right? I was looking for 4, I found 3. Now that's not the answer to my query. The answer to my query should be 9, but now that I'm at 3, this is the largest thing that's smaller than what I'm looking for. Well, then the smallest thing that's larger than what I'm looking for is just the thing that comes after it in this list. And we can try that for another one. For instance, if I want to look for, let's say, 2. 2 is 0, 0, 1, 0. So that follows the 0, then the next 0, then the 1, and then it tries to go to the left child, but there is no left child, there's only a jump pointer. And that jump pointer, so since there's no left child, the jump pointer points to the smallest thing in the right subtree. And that smallest thing in the right subtree is actually the smallest thing that's bigger than what I'm looking for. And so that actually gives me my answer immediately. I don't even have to navigate in this list. So if a subtree is missing, if a right subtree is missing, like here, then it points to the largest thing in the left subtree. And if a left subtree is missing, like here, then it points to the smallest thing in the right subtree. Right? And that makes sense because, right, if I'm going left and I can't, so there's nothing there, well, that means, well, the thing I'm looking for is definitely not there, and there is actually nothing there that has the same, that has a 0 bit in that place, but there is something that has a 1 bit in that place, and then the smallest thing that has a 1 bit in that place will be the thing that comes right after the thing I'm looking for. Okay. All right. So, so that's how find works. And now we should just make sure that that adding and removing continue to work. So let's see. If I want to add something, let's try it and see if we can get it to work. I don't know. Let's add 15, that's a good one. 15, that's 8 plus 4 plus 2 plus 1. So we go right, we go, that's for the first one, we go right again for this one. Now we want to go right, but there's nothing there. There's only a jump pointer there. And we eventually want to, we want to insert this thing, so we have to put a node there. So let's forget about the jump pointer for a second. Put the node there that we need. Now notice that this doesn't need a jump pointer anymore because now it's going to have 2 children. So we really can forget about this jump pointer. And so this gives us a 1, 1, 1 star node. And then we want to go right again. And that gives us 15. Okay. Now, a few things we need to do. We need to update the jump pointers, and we need to insert this thing into the list at the bottom. So let's look at inserting into the list first, because we should have done it already. So when we were inserting 15, we got to this stage, and we wanted to go to the node at the right child, but it wasn't there. There was only a jump pointer there. So we have to make these nodes, but that jump pointer, what did it point to? Well, it pointed to the largest thing in the left child. And if we think about that for a few seconds, you'll realize that, oh, that is the thing that comes just before 15. In the linked list, in sorted order, that thing that the jump pointer pointed to was the thing that comes just before the thing we're about to insert. So let's remember where that jump pointer pointed to. And we insert all of this. So we create these nodes. And we still remember that the jump pointer was pointing to this node 12 in our linked list. So now we have a pointer to a node in the linked list that comes just before the one we want to insert, and we insert it, right? If you have a doubly linked list and you have a pointer to the node just before the one you want to insert, it's easy. You just splicing it in. So from the jump pointer that we erased here, we just save it, and that allows us to put this thing in the list. And then we created a whole bunch of new nodes, this one and this one, but in general it could be a lot of new nodes. And each of those new nodes that we created has only one child, so it should also have a jump pointer. But that's easy. We know what those jump pointers point to because, for instance, this jump pointer should point to the smallest thing in the right subtree, but there's only one thing in the right subtree. It's just the thing we just added. So, and similarly, if there were more nodes we created like that, all of them would point down to this thing. So adding that way is easy. Okay. All right. So that's the add operation. So one scan down. As soon as you leave the tree, so leave the existing part of the tree, you have to start creating new nodes. But remember that jump pointer where it pointed to. Once you're done creating those new nodes and you've got the node in the bottom, use what the jump pointer was pointing to do insertion in the linked list, and then just walk back up and update the jump pointers on the new stuff that you just created. Right. So the really generic picture looks like this. This is before you did the insertion. After you do the insertion, so you're going to create something like this, and that thing in the bottom is going to get spliced into the linked list right there. That's what happens if you do this insertion and you leave, you get to a place where there's no right child, and if you get to a place where there's no left child, so that's a picture that looks like this. Before you did the insertion, there was a jump pointer that pointed to the smallest thing in the right subtree, and then after you do the insertion, you've created a whole path, and that's where you insert into the linked list. Okay. All right, and what about if we want to remove something? I don't know. Let's do an example. Let's remove 9. So in order to remove 9, I first want to find it. So I find it. And let's remember, once we find 9 down here, it's part of this doubly linked list. So we actually know the two things that bracket it. 3 is the largest thing smaller than 9. 12 is the smallest thing larger than 9. Let's just remember those. You can store pointers to those things in some local variables. So we want to splice it out of the linked list. So we want 9 gone. And now we want to walk back up, and we want to walk back up and look at each node, so after we've deleted 9, and see if that node has any children. And if it doesn't, we need to get rid of it as well. So for instance, this node here, its only child was 9, and we just deleted 9, so it has to go. So we delete it. Now this node here has no children anymore, right? Its only child was this this other node, so it also has to go. Now finally we get up to this node, and this node still does have a child. So it used to have 2 children, now it only has 1, but because it has only 1 child, that means it has to have a jump pointer. And where are we going to get that jump pointer from? What is it going to jump to? Well, this node here, in this case it's missing a left child. So that left child should point to the smallest thing in the right subtree. Where is that? Well, that's 12 here. And remember, when we removed 9 from this linked list, we kept these 2 pointers to the largest thing smaller than 9 and the smallest thing bigger than 9. And in this case, because we're missing a left child, what we want this jump pointer to point to is the smallest thing that is larger than 9. That's this one. So we have what we need to fix this jump pointer. And at that point we stop, because this node still has a child, it doesn't get deleted, and nobody else's jump pointers change anymore. And you don't have to worry about anyone else who had a jump pointer that pointed to 9, because if they had a jump pointer that pointed to 9, the node we just deleted, that meant that they only had 1 child, and 9 was 9 was the basically such a node gets deleted. So that those nodes that had jump pointers pointing to 9, there was 1 of them in this example, actually 2 of them, they all get deleted. All right, so that's a binary trie plus jump pointers plus linked lists. And in that structure you can add, remove, and find. How long does all of this take? Well, it's all pretty simple stuff, right? You just start at the root of the trie and read off the bits until you either get all the way to the thing you're looking for, or you get to a jump pointer that takes you almost directly to the thing you're looking for. That's for finding. And then if you want to add and remove, that's just followed. That's basically 1 pass down the tree, and then maybe a pass part way up the tree to update either jump pointers or to delete nodes. But the height of the tree is W, and I don't think it's hard to see that you can do each step in constant time. So you can add, remove, and find in O of W time. Okay. So let's write down what we've got here. Binary trie, I'll call it the binary trie plus plus. Sorry. And add takes O of W time, remove takes O of W time, and find takes O of W time. Okay, that seems not bad. Sort of like we can find things pretty much, we can do these operations as fast as we can read off the bits 1 at a time from our integer. So that sounds impressive, but actually, wait a minute, maybe it's not so impressive. Remember that we're trying to beat O of log n. So here n is the size of the set. And what's W? Well, W is the number of bits in our integers. So, wait a minute. How many W-bit integers are there? There's only 2 to the W of them. So the number of distinct W-bit integers is only 2 to the W. So that means the size of our set can't be more than 2 to the W. If I take the logs on both sides, that means the log of n, log the size of our set, is less than or equal to W. So this is not impressive at all, right? This is never better than log n. Even if I store every possible integer, then W is then exactly equal to log n. So that's not impressive at all. But maybe we can do better. And to think about how we can do better, well, one thing we should realize is we should have seen this problem coming, that we weren't really going to be able to do better this way. And why is that? Well, that's because we made this binary tree, and in particular, every time we make a decision, there's only 1 or 2 outcomes, right? It's because we read a bit and we go left or right. That's basically every decision we make is driven by reading a bit of this thing. Okay. So every decision that we make is a binary decision. There's only 2 possible outcomes. And on the other hand, for instance, when we do a search, there's going to be n plus 1 possible outcomes, right? You could be smaller than everything, or between 1 and 3, or between 3 and 12. So if there's n things in here, there's n plus 1 possible outcomes for a search. And then you could convince yourself, well, if you only make binary decisions and there's n plus 1 possible outcomes, then you have to make at least log of n plus 1 decisions at some point. So, the sticking point here, the thing that's slowing us down, is we're only making binary decisions. So we need to break out of that somehow. So we've seen a couple of ways to do that. One of them was when we looked at sorting. Sorting had the same problem. If we stick with comparison-based sorting, comparisons only have binary outcomes. A is less than B, or A is bigger than B in general. So there we saw that, yeah, that means comparison-based sorting algorithms can't take n log n time. But then we saw sorting algorithms that were specially for integers, and they were faster. And how did they become faster? Well, they did that by taking those integers and using them as indices into an array. So that's really, and that made them faster. And the reason that gets around the problem of making only binary decisions is when I take an integer that you give me and I use it as an index into an array, if the integer is in the range 1 through k, then that is a constant time operation that has k possible outcomes, and k can be much, much bigger than 2. And the other place that we've seen this is in hashing. There we actually saw an even more pronounced effect, where if I look for, so remember the underlying technology of hash tables is to store integers. So you turn objects into hash codes, which are just integers, and then you basically store those hash codes. That's where the interesting, or I mean, that's one part of the interesting stuff happens. And there we saw something really impressive, is that it doesn't matter how many integers you give me, I can find them in constant time. So if they're there, I can find them in constant time. Unfortunately, if they're not there, you can't find anything. maybe we can do something with that. All right. So, for example, when we searched for 3, or when we searched for 4, somehow that search was actually quite fast, in the sense that when we searched for 4, we went 0, and then we tried to go 1, but there was no right child there, and that immediately took us to the bottom list, which almost took us directly to the answer. I mean, then we only have to see whether we need to look to the next one or this one. Okay. So somehow when we searched for 4, as soon as we got to here, the whole game was over. We got right to the bottom and we won. Similarly, if I was to search for, well, if I was going to search for 9 now, 9 is this one. 9 is 1, 0, 0, 1. There it is there. So that would go 1 and then try to go to 0, but 0 is not there. So it immediately follows the jump pointer and it finds 12, which is the answer you're supposed to get when you search for 9. So somehow these jump pointers, they're not only useful because they give you somewhere to go, but actually they tell you exactly where to go. Once you get to the node where you follow a jump pointer, you're happy, you're done. So what we would like is to do a search that finds it doesn't really directly go to the bottom list. Instead, it tries to find where you would follow the jump pointer and find that more quickly than it would otherwise. And this is where something a little bit mind-bending happens. So we're not going to search directly we're not going to search directly in this tree top-down like this. Instead, we're going to do binary search on the levels of this tree. Okay? So we're going to ask the question. So for example, let's look, let's use the example of 9 again. So I've deliberately labeled the internal nodes of this thing with strings that start out with a sequence of 0s and 1s. That's sort of everything that leads to this node starts with a 0, everything that leads to this node starts with a 1, everything that leads to this node starts with a 0, 0, over here it's a 1, 1, over here it's a 1, 1, 0, and then star, meaning some other stuff comes after that, but it doesn't matter what that stuff is. So here I look for, when I'm looking for 9, so I could ask, well, if I was to do the search from the top down for 9, and if I did that, I'm not going to do it, but if I did, would the search make it to this level here, or would it be done before that? So we've seen the example, and we know that the search won't make it to this level, because when we search for 9, we hit the jump pointer before we get to this level. Okay, that's what we get by looking at it, but is there another way to understand why the search doesn't make it to this level? Well, the search doesn't make it to this level because 9 starts with 1, 0. And if we look at the nodes at this level, there's one that starts with 0, 0, and there's one that starts with 1, 1, but there's none that start with 1, 0. So that means there's nothing in our set that starts with 1, 0. And so if we try and follow the path for that, we're going to fall out of the tree before we get there. Okay. All right. So if someone would just tell us So at this level, the labels have 2 bits in them and then some stars, but just keep the bits in mind. So at this level, there's a set of these 2-bit labels. In this case, it's 0, 0, and 1, 1. At this level, so there's another set. In this case, it's 0 and 1. This level, there's nothing. It's not exciting at all. Down at this level, we have 0, 0, 0, 0, 0, 1, this one, 1, 1, 0, and 1, 1, 1. And then at the bottom level, we have the actual elements themselves. Not so important. Okay, so I'm looking for 9, and start at this middle level here. And there's a set associated with that. There's sets of 2-bit integers. Now 9 starts with 1, 0. And I ask, is 1, 0 inside this set? The answer is no. And that means that if I was following the path for 9, I would have hit a jump pointer before I got to this level. And I'm looking for the level where that jump pointer is. So that means the level where the jump pointer is somewhere before this. It's up here. Well, okay. So now binary search is a bit boring on 2 things like this. So now I look, let's say, at this level. Now this level, things are labeled with 1 bit, just the leading bit. So I look at the first bit here, it's just a 1, and I say, is there something in this level that, in this set here of labels at this level, is 1 in there? Yes, it is. And in fact, here's the node that starts with 1. Okay. So let's see what I've figured out so far. I know at this level there's a node that starts with 1, and at this level there is no node that has a 1, 0. So that means that this node has no left child, so it has a jump pointer. And in fact, this is the node that has the jump pointer for 9 that I need. Now, let's just quickly do another example. 14. 14 is 1, 1, 1, 0. Start in the middle and ask, is there a node at the middle level that starts with, that's labeled with 1, 1? Yes, there is. Okay, that's good. That means whatever I'm looking for is going to be here or further down, so at these lower levels. So now let's go to the middle level of whatever it is that's left. So that's this one, and I ask, okay, at this level they have labels of length 3, so I look at the first 3 bits, say, is there a node that starts with 1, 1, 1? Yes, there is. It's this one. So that means that the answer that I'm looking for is going to be either, the jump pointer that I'm looking for is going to be either here or at some level further down. So now I try this one, and I ask, okay, is there a node at this bottom level which is labeled with, so at the bottom level they have 4 bits, which is labeled with all of this, 1, 1, 1, 0. And the answer is no. There's no node at that level with that label. There is one that's labeled 1, 1, 1, 1, 1, but none, there's no 14 there. So what I learned is, if I followed the search path for 14, I would make it to this level, but not to this level. that means at this level, the node here is the one with the jump pointer that will take me to the answer. Okay. And indeed, that's the case. You get to this node and follow its jump pointer. That takes you to the answer for 14. And of course, if you search for something that is in the set, like 12, then at the middle level, it'll say, yes, there is something that starts with 1, 1. At this level, it'll tell you, yes, there's something that starts with 1, 1, 0. And then at this level, it'll tell you, yes, there's something that starts with 1, 1, 0, 0. And it's exactly the thing you're looking for. So what I just described is binary search on the levels, right? You pick the middle level, and either you learn that, okay, you need to look above it, or you need to look at this level or below. So that means that I can do this, if there's W levels, binary search will only take log of W steps. Okay, good. But what's a step? Well, a step in this binary search is there's a collection of labels across the level, and I need to know, like, this is the collection for this middle level. I need to know if the thing I'm looking for, if it's, in this case, first 2 bits are in that collection. And I need to know either yes, and if yes, which node are they in? And if no, I'm happy with just the answer no. Because if the answer is no, then I know that I need to look higher up. So I need a data structure that stores these things and will allow me to search for them. And if it's there, it will tell me, yes, it's there, and give me the data associated with it. And if it's not there, it will just tell me, no, it's not there. But that we've seen, right? That's what hash tables do. Or if you like, that's what Java maps do. You store keys associated with values. So these are the keys. The values are the nodes. We can look in the map and say, does it have this key? And the answer might be no, in which case we can't do anything more. But if the answer is yes, we can ask, okay, which node has this key? And remember, maps, which is just implemented by hash tables, they can do that in constant time. So even though in the middle level there could be thousands of nodes, we can know in constant time whether there's a node that matches the first half of of the integer we're looking for, the first half of the bits in the integer we're looking for. So in constant time, we need to know whether that'll tell us whether we need to look higher up or whether we need to look further down. So that means we're doing binary search, and each step of the binary search runs in constant time. And it's binary search over the W, that's actually W plus 1 levels. So that means that the whole thing runs in O of log W time. Okay. Good. So this binary trie, if we just add these hash tables, or maps, if you like, at each level that store the labels of the nodes, so these are the sort of prefixes of the strings that lead to the binary strings that lead to those nodes, then that speeds up our find. And it speeds up our find not by a small amount. Find goes from being O of W time to O of log W. Okay. So we'll call that the binary trie. So everything that we did up here plus hash tables for levels. right? Now, this is a lot faster than this. Some people would say that log W is exponentially faster than W. And they'd be right, in fact. So for instance, here, when W is 32, log W is 5. When W is 64, log W is 6. And when W is 128, log W is 7. So, for 128, for instance, 2 to the 128, I think that might be more than the current estimates on the number of atoms in the universe. So that's a really big number. There's a lot of 128-bit integers, huge number of them. And this says that you give me any set of 128-bit integers, I can store them in this data structure so that in 7 steps you can tell me whether something is in the set. Okay. So, you know, take the integers in the universe and assign each one take the atoms in the universe and assign each one an integer, and then you can give me any subset of the universe, and in 7 steps I'll tell you whether or not the one you're interested in, the atom you're interested in, is in the subset or not. So that's remarkable. So it doesn't matter how big the subset is, the only thing that matters is that the size of the universe is 2 to the 128. All right, so that's find, but what about the other 2 operations? Well, the other 2 operations, unfortunately, not much you can do for those. So they work pretty much exactly as before. The only difference is when I do an insertion, so when I add something, remember that creates a new path of nodes, like in this picture. Then there are, remember at each level in your tree now, there's a hash table that stores the labels of the nodes at that level. So when I create a new node here, I have to add it to the hash table for that level. When I create a new node here, I have to add it to the hash table for that level, and so on. So when I add something, it creates a whole new path of nodes. I then have to add everything in that path to the hash table for that level. And similarly, when I remove something, remember when you remove something that takes away a leaf, and then maybe its parent has no more children, so you need to take it away, and then maybe its parent has no more children, so you need to take it away. Well, those nodes at each of those levels were in those hash tables. You have to remove those labels from those hash tables. But I mean, you can add and remove from hash tables in constant time, so that doesn't increase the running time of add and remove, but unfortunately there's still O of W. So this greatly speeds up the find operation, but it doesn't speed up add and remove. All right. Can we make these faster as well? Well, I wouldn't ask the question in the context of this course if the answer was, I guess I could ask it if the answer was no. But the answer is yes. And let's see how we can do that. So now we're going to take a step back. So what have we got? We have this thing here So this doesn't really have a good name, but this one does have a name. It's called the XFast try, because it's so fast for searching, but not for adding and removing. So we know that we can make an XFast try. That means its height is W. It can find things in log W time, but it can only add and remove in O of W time. So here's the plan. We put some of our data in the XFast try, but not all of it. Right. So when we put some of the data in the XFast try, that gives us, this at the bottom level. There's this linked list with whatever subset of data is in there that stores this stuff. But with each of those, we will put a little bag of data. Right? So, and maybe with the last one we have to put 2 bags of data. Right, so we have some of our stuff is in this XFast try, and then this one over here has a bag that contains all of the values that are smaller than it. This one has a bag that contains all the values that are smaller than it, but bigger than the one that came before it, and so on. So if you think of this on the number line, these are the bags that are in these are the values in the XFast try. But between those values, between consecutive ones, you will find other stuff. All right. And how much other stuff? Well, I will set it up so that between 2 values here, there should only be O of W things. So not all of the data is in the XFast try. Most of it, only about 1 out of W things is in the XFast try. Most of it lives in these bags down here. And these bags, they will have size only O of W. So how do I store these bags? Well, the bags are not very big. They only have size O of W. So the bags should be a data structure that stores a set of W things so that I can search for things and add and remove in log W time. Well, that's easy, right? That's this thing. Take any of our sorted sets that we've done before. If they store n things, they can do all their operations in log n time. We're just going to make them so small that they only store W things, so they can do all their operations in O of log W time. So we have an XFast try on top, and we have binary search trees here, or whatever you want. Treeps, skip lists, whatever you want. Scapegoat trees, you name it. All right, so what happens now? Let's see if this can do find operation the way we would like it to. So for a find operation, we are looking for some value x. We search in the XFast try, and we find x, okay. And by searching in the XFast try, we find that x lies between this value and this value. Or maybe x is equal to one of these values, in which case we're done. But the interesting thing is when it lies in between these two values. Okay. So maybe the next thing that comes after x is this black thing here. Or maybe it's inside this bag. So then I just search for x inside this bag. This bag is a binary search tree, or a skip list, or whatever your favorite thing is. And I get an answer in here. Or I get that it's actually bigger than everything in the bag, in which case the answer is this thing up here. So it's one search in an XFast try. That takes O of log W time. Plus one search in a binary search tree whose size is W, which takes another O of log W time. So this thing that I'm describing is called a YFast try. And we see that actually, when you break up things into two levels this way, it's a fast search and then another fast search. So the constants go up, but so maybe it's 2 times log W, but that still doesn't change the asymptotic running time. It's still on the order of log W. All right. Now what about adding and removing? Right? We could already do find quickly. What about adding and removing? Well, why would that be faster to add or remove things? Well, here's the, there's a few ways to do this, but I will just describe, I think, what is probably the simplest one. Let's say when I add something. So when I add an element, I will imagine tossing a coin. But it's not a fair coin. So with probability, so when I do add x, with probability 1 over W, we will add x to the XFT. And with probability 1 minus 1 over W, we just add x to a bag. So most of the time, we just add. When we want to add x, we search for it. We find it lies in between two values in the XFast tree, and that means we want to put it into the bag that's between those two values. That's just it, adding it to the binary search tree that's storing that bag. That's easy. So that's what happens most of the time. But every once in a while, we toss this coin, this bias coin, and it comes up heads with probability 1 over W, in which case we're not going to just add x into one of these green trees, but we're going to stick x in the XFast tree. So that looks like this, something like this. New x is going to go into the number line here, which means we also need to split this bag, right? So there used to be a bag that contained all the elements between these two, and now I'm adding x, so that bag needs to get split into 2. So, right, this was a this was a sorted set that contained O of W elements, and now I need to split it into two such sorted sets. That's easy, right? It depends which data structure you're using. And in fact, you can certainly do it in O of W time. Just take everything out of your sorted set in sorted order, break it into two pieces at X, and then make your sorted sets again. So, right, if you use skip lists, for example, really all that means is you take their list, find where X is in the bottom list, and then cut your skip list into two things, starting from there. Sort of easy operation. Okay, so that's not a big deal. You can certainly do it in O of W time, but actually you can even do it in O of log W time. All right, so then what's the big picture? If this is my rule for adding, and well, let's just say that's my rule for adding. And what's my rule for removing? Well, for removing, I don't really have a choice. Someone asks me to remove something, and either the thing that I remove is found in one of these trees here, in which case I just remove it, or the thing that I remove is actually in this XFast tree here, in which case I remove it from the XFast tree. For instance, maybe this is the thing that I have to remove. And then what happens is there were two bags down here, like if this is what I'm removing, there's these two bags which need to be merged into one bag. And that's not hard. I mean, that's just taking, if you like, two skip lists, where all the elements in the first skip list are smaller than all the elements in the second skip list, and gluing them together back to back, side by side. It's not a difficult thing to do. So what can happen is when I add, sometimes a bag might have to get split, and when I remove, sometimes two bags might have to get merged. So why is all of this efficient? Well, in particular, I said the size of the bags here is O of W, but I never guaranteed that. And what happens if I keep adding things and they all keep going in the same bag? Then the bag gets bigger and bigger and bigger, and then it's not true that the size of the bag is O of W. But can that really happen? Well, if I keep adding things to the same bag, each time I add something, it has probability 1 over W of not going in the bag, but actually going up and splitting the bag into two. So intuitively, a bag can't just grow and grow and grow, because after it's seen about W, once it grows to size about W, I mean, even in the first W things that try and go into a bag, it's likely that one of them will have caused the bag to split into two smaller bags. So that's one way to think about it. But a more general thing the more general picture is, what's really happening is there's a whole set of things that I'm storing, n things, x1, x2, x3, x4, all the way up to xn. So that's all of the stuff that's stored in my data structure. And for each of these, when I inserted it, I tossed a coin that came up heads with probability 1 over p. And you can imagine those things, those are the ones that live up here in this layer. And if you think about that, so, one of these things pops up here, And now you say, okay, well, the one that popped up here, there's a bag between it and the next one. How big is that bag going to be? Well, between it and the next one, there's a bunch of things that happened. And everything that ends up in this bag is because I tossed a coin that did not come up heads. So that with probability 1 over W, the coin comes up heads, and with the remaining probability, it doesn't come up heads. And so the number of things in this bag is 1 less than the number of times that I expect to have to toss a coin that comes up heads with probability 1 over W before I see a heads. And if you were in my class this morning, what you learned is the expected number of things then in this bag is at most W minus 1. Okay? So the expected number of coin tosses is W, but the last one actually doesn't go in the bag. It comes up into the structure here. And if you weren't in my class this morning, that's okay too. That's the idea. Much in the same way that when we were looking at skip lists, we would sometimes look at a particular layer and and the layer above it, and then ask how many things were there between something at this layer up to the thing at the next thing that made it into the layer above. The answer was 2, or 2 including the thing above. And in general, that's because in skip lists we were tossing coins with probability 1/2. If we change that probability to 1 over W, we'll get W minus 1. So that says when I go to one of these bags, its expected size is W. So good, that means I can add or remove from that bag in log W time. And now if I look at how long does it take me to let's say add, so expected running time of add, well, 1 over W time, I have to add to the XFast tree. That's slow. That takes O of W time, so that's the probability of having to add to the XFast tree. And the rest of the time, I don't have to add to the XFast tree, I just have to add to one of these things. So that's O of log W. Well, 1 over W times W is 1. This is not bigger than 1, so in total this is only O of log W. And a similar thing happens with remove. So when I remove something, either I get to remove it from just remove it from one of these bags, one of these little green trees, which is just O of log W time, or I have to remove it from the XFast tree, which takes W time. But again, the things that are in the XFast tree, so the probability that the thing that I want to remove is in the XFast tree is just 1 over W, because when that thing was added, we tossed a coin for it to decide whether it was going to be in the XFast tree or not, and the probability that that coin came up heads, that the thing was in the XFast tree, is only 1 over W. So as long as somebody is not looking at my data structure to see which are the bad ones to remove, then the probability that they're going to remove something that's going to be slow in this XFast tree is only 1 over W. So you get the same analysis for add and remove. Okay. So that means that you can add, remove, and find things in this YFast try data structure, and the expected running time for each of those operations is O of log W. So these can be enormous integers, right? So, you know, if you don't like, if you think 128 is not enough, go up to 512. So that means you can have sets of size 2 to the 512. It's an enormous number. That's definitely more than the number of atoms in the universe. And you can look up something in that set to know if it's in the set or not. You can look up any integer, and it'll only take you, 512 is 2 to the 9. So only take you 9 steps. So 9 hash table lookups, and then a search in a binary search tree. Okay, good. Someone asked the question, is the final exam 3 hours in length? No. I don't know why Carleton has scheduled that. We asked them for a 2-hour final exam, and that's what it will be. So it's going to be a 2-hour final exam. It's a bit strange because scheduling final exams now has nothing to do with any central scheduling service. I mean, they can give us the time slot, but the number of hours is, I mean, it's us who implements the exam. So the final exam is 2 hours. Okay, so that's what I wanted to show you today about these incredibly fast data structures for searching in integers that are, yeah, if you really need something super fast for searching integers, they are they can't be beat. All right, so that's a good place to leave it today.